As a first simple example, let's take the extension generated by two quadratics, joining the square root of 2 and the square root of 3. So our aim is to show how the Galois group corresponds in this picture. So these extensions are all of degree 2 because the minimal polynomials are x squared minus 2 and x squared minus 3. So the total extension has degree 4. So therefore we would expect, if this were a Galois extension, to have a Galois group or an automorphism group with 4 elements. Now we can write down two different automorphisms. The one can be defined, say, by sigma, which maps square root of 2 to minus square root of 3 and keeps square root of 3 fixed. And we can define another one, tau, which keeps square root of 2 fixed and maps square root of 3 to minus square root of 2. So can you figure out which of the two fields, q square root 2 and q square root 3 in the middle, are the fixed field under sigma and tau respectively? But clearly, the correspondence on the group side, so at the very bottom we will have the full Galois group, which is the group generated by sigma and tau. This will be the Galois group of the big extension over Q. At the very top, we will have the group consisting only of the identity element and the fixed field of E under the identity is E itself. So now we need to fill in the two subgroups in the middle. So let's see. Does sigma fix square root of 2 or square root of 3? It fixes the square root of 3, therefore on the right-hand side of our picture we've got the group generated by sigma, and on the left-hand side we'll have the group generated by tau. Tau fixes square root of 2 but not square root of 3. So you might realize that there's something missing. What is the structure of this group generated by sigma and tau? Sigma and tau each have order 2, so the group can't consist solely of the elements, the identity, sigma and tau. Those are 3 elements. So there's one element missing, and the element missing is sigma tau. So what does sigma tau do to square root of 3 do? It maps square root of 2 to minus square root of 2, and it maps square root of 3 to minus square root of 3. Now the question is, what is the fixed field under this group? So we can fill in this picture, and we have a third subgroup, one generated by sigma tau, which happens to be equal to tau sigma in this case. So the group is the Klein 4 group, which has 3 subgroups of order 2. What is the fixed field under sigma tau? Well, in order to work this out, normally one would write out a basis for the big field over the small one. You would say that q square root 2 square root 3 is generated over q by the element 1 square root 2 square root 3 and square root 6. Because square root 2 times square root 3 must also be in this. And if you look at this quickly, you will see that actually square root 6 is fixed by sigma tau. But to be a little bit systematic, let us say what sigma tau does to an arbitrary element of this field. It maps a plus b square root 2 plus b square root 3, b square root 6 to a minus b square root 2 minus b square root 3, and then 6 is 2 times 3, so we get 2 minus plus b squared. So if the input and the output of this automorphism are to be the same, b and c must both be 0, and a and d can be arbitrary. That the fixed field of this big field under the element sigma tau is exactly the span of the elements 1 and square root 6, and that is exactly the quadratic field. So to complete our picture, we fill that in the middle of the diagram. And we have a one-to-one correspondence between intermediate subfields and subgroups.